Hello, everyone. Welcome to IO Extended UK and Ireland. So IO Extended is organized by Google developer groups. And to give you a better idea of what Google developer groups are, I'll play a short video.
Technology brings us closer together, even when we're far apart. Google developer groups host meetup events for local technologists to connect, learn, and grow with others in their area.
The project I'm mostly proud of would be teaching introduction to programming to 7 girls in my hometown.
In the GDG, I used to attend various workshops, like it was on Firebase, Android, Cloud. Everyone is learning from someone else.
We started to meet twice a week for a long time, learning Google Cloud. Amazing experience.
After joining Accenture as a software engineer, I started to share my journey in Medium, podcasts, and talks at online bootcamps.
My talk inspired one of community members a lot. So I mentored him to start his startup path. And 1 year later, at the same conference, he was giving a talk at the same stage.
One member of our community moved from being a DJ at our event to a developer in the first leading bank in the country.
When we do events that impact a lot of people, we are bringing opportunity to our region. So a lot of investors, a lot of startups, they will start to see opportunities here.
Okay, so just to recap on what you saw in that video, Google developer groups are local online or in-person meetups for developers to connect. So this global community prides itself on being an inclusive environment, and that means that everyone and anyone interested in technology, from beginner developers to experienced professionals, are welcome to join. It is a developer community program supported by Google and Google developers. So now I'll tell you a little bit about IO Extended and UK and Ireland. It's IO Extended UK and Ireland, split into two parts of explanation. So IO Extended events are organized by Google developer groups across the world as a follow-up to the main Google I/O event, which happens annually. And currently, you're in the UK and Ireland Google developer groups. So this one is composed of 17 Google developer groups, one developer student club, and one SRE group from UK and Ireland, and we're all working together to organize events for you. So the IO Extended UK and Ireland has 9 separate tracks split over 3 evenings. So today is the first evening of the event, and there's 3 tracks on each evening. If there's any talks you would like to see, just have a look at the broadcast at the YouTube channel that you're watching this broadcast on for the other tracks. And feel free to switch between them as you wish. Now you are on the AI NML track, just location-wise. So there'll be 3 AI NML talks following shortly after this introduction. So some housekeeping. There are 4 hosts for you today. Myself, Jana Hoksava from GDG Galway, Shalki Nakpal from GDG Dublin, so we're the Ireland representatives, Pragati Mishra from GDG Glasgow, and Ricardo Diaz from GDG London. As mentioned earlier, this is an inclusive environment, so we ask you to have a read of the code of conduct that can be found at devparty.io/code of conduct. And we of course encourage you leaving comments, questions in the comment section, but comply with the code of conduct. Yeah, so finally, we're just getting started. The agenda for this evening is first off, we'll have Karthik talking to us about Keras design patterns. Next, we will have Matthias talking about explainable AI beyond SHAP. And finally, we will have Google's Carol talking about AI-based analytics in the cloud. Finally, at the end, we will have a 15-minute session for any questions you might have. So, like I said, feel free to post them in the comment section anytime as during the event, and we'll try to answer them all. We'll look forward to that too. So, finally. We have a hashtag you can use if you're commenting about this event. I know it's not in person, so it's hard. It's not an in-person event, but to try to make it more social, to get closer to other people from all over the world that could be watching this, use the hashtag Google I/O Extended UKI to post about your experience. Now, I'll run through those a little bit too fast, so I'll bring in one of our hosts today, Ricardo.
Hello, everyone. Nice to meet you all. Thanks for joining today. So yeah, I mean, the event should start a little bit around 5 minutes or so. Our speaker is on the back waiting. She's preparing everything for the talk. So yeah, we'll be here waiting for you guys. We also would love to know about your experience with online events, and if you're keen to start going to in-person events. We would love to make this one an in-person event at some point, or something like that. Yeah, so right now, I mean, we still have 5 minutes for Karthik. He's getting ready.
And we'll take this opportunity to tell you that you could join us at other events that we organize throughout the year. We do once-off events. There's workshops. Regard around 2 workshops for us. Those are fun.
Yeah, you can also check all the other content that is available online in the channel. This event will be also there in the channel for you guys to recap if anything you missed anything. You can recap and go back and watch it. Watch Karthik talk or Carl talk. I think those are. I think all the 3 talks are quite interesting in terms of AI ML. I'm personally a machine learning engineer as well, and I think all the exciting technologies like Keras, Karthik is going to talk about soon. I think that one is quite interesting, and then Carl's coming up as well, and we will see how it goes. I think it's going to be quite fun for us, and I mean, I'm pretty excited to know what are they. And also, make sure to, if you have any questions, post it there. We will try to answer as much questions as we can. Yeah, I mean, we will be here in the back if anything happens. All the events, something always happen. So hopefully there will be no interruptions for this event. But yeah, I mean, we're gonna be here, and in any case, so yeah, I think Karthik is already putting up the slides on the back, yeah. So
I will share advice with anybody who hasn't spoken much before in public. do not speak too fast, for you will run through 50 minutes of content within 10 minutes.
No, I think the housekeeping is quite short. The video was also great at the beginning. Sometimes you calculate in the time and speaking, it's quite it's something you need to get a hang of it. But I think it is. It's what we have in the events. Right now, we also missing some hosts that will join us. You'll meet them next. So we keep going, and the talks are going to be quite interesting. So looking forward to them.
It's a nice range. To say I'm happy about all our speakers. They provide a nice range of topics.
Quite a hard time looking for them as well. But we managed to get a good ones for you guys. Hopefully you would like all the talks, and we kind of did a bunch of research and reached out to a lot of good speakers. We managed to get really good ones for these talks. So really looking forward to all the talks, and it seems like Kartik is almost ready. He's here with us, so maybe we can pull him in to the chat as well. Still, we have 1 minute, but we can do some introductions as well.
Then
Chatting a little bit. Yeah.
Hello. Hi.
Hey, Hardik, welcome. Welcome to IO Extended.
Thank you for having me here.
Kartik is joining us from Mannheim, which is in Germany. There. Will we let you take it off? There we go.
All right. Yeah. Thank you. Wonderful. So hello, everyone, and welcome. So I wish we had this entire GDG extended in person, but it is what it is. I think we are all there. If you're just hanging there, I hope you got your vaccinations and we're all set. I think probably next IO extended, we should be having this in person. Everything is fine. So just hang in there. With that, I think I will get started with today. Before that, I will also give you a quick introduction to myself. So as Jana mentioned, thanks, by the way, for the introduction, Jana and Ricardo. I live in Germany, in Mannheim, and I actually work for SAP, where as a senior data scientist, and I'm also I'm actually a GDE, a Google Developer Expert in machine learning, and I've been working with the team for quite some time now. So it's a lot of fun, and what we do is we share some interesting ideas, new, all the things that comes up new in TensorFlow and in machine learning in general. And today we will be talking about one such thing, which is basically also something that's very important to me, I think, because we hear about machine learning quite frequently, but more often the trouble is that generally people try out some examples, and invariably it does not translate well into, say, something like if you want to bring it into production, if you want to make it enterprise ready, into basic software engineering, then it becomes a challenge. So what I thought would be really useful for people who are especially used to doing keras or using TensorFlow would be to basically share some design patterns. So if you're a software engineer and if you already have some experience with TensorFlow and keras and so on, then generally these patterns would be really useful for you, especially if you're trying to build on some existing framework or build on some existing code as well. So with that being said, we will see what are the sections, the broader sections, broader areas that we'll be looking at. The first part would be talking about the sequential API, what Keras already offers. We will be talking about basically how this sequential API is good and why do we need functional APIs, and how it actually provides some level of customization, and how could you even take that even further and then fully customize the code, say, for example, for the train step, or how do we completely customize it and then make it your own. So this is also where Keras provides this level of flexibility starting from out of the box into some level of customization into complete customization. So this is how this entire presentation is sort of organized. So with that being said, we will talk about the sequential API. So the sequential API is more where actually, as you already probably know, Keras does not actually generally force you into, a sort of like a structure into how do you train your model or how do you, infer model, generally the workflow, the machine learning workflow, as well as, how do you control the high level as well as, say, the low level code that you would like to, have in your machine learning algorithm. So this is more in tune towards where, at the high level you could use it somewhat similar to what you could do with scikit-learn, for instance, where you just take a model, just do a model.fit, and then basically the framework will do its thing. It's basically the framework will figure out if there should be a validation, the loss functions, and so on. All that will be taken care by the framework itself. So it lets you do that as well as basically to the level of, say, like NumPy, where you can take every single detail, you can rip it apart, you can actually sort of use that to make it, put it together and then completely customize the entire training. Um, this is what so most researchers, if you're especially doing with something to do with machine learning, then you would like to have, say, custom loss functions or custom ways in which you could expose the training function as well. So these are the ways in which, or probably you would like to have custom callbacks, for instance. These are really useful, especially once you have the basics of Keras ready for you. Then you can start to dig deeper, and then you'll also start enjoying what the framework actually offers in terms of how you can customize it. So with that being said, I will quickly share what we are going to talk about today. So we will quickly introduce like an autoencoder framework. So I think this is very easy to understand. You don't have to necessarily be, have an idea about computer vision or, actually you could also, be completely working on NLP techniques for that matter. The idea here would be to expose, how the entire framework would look like and how to, gradually get into, fine tuning it into how you would like to use it. So in general, an autoencoder here would be, something like where you would have some input, say, for instance, an image over here, which would then be probably compressed or, be encoded into some sort of like a latent representation in the middle, as you see after the encoder. And what happens is that the decoder then uses this latent representation to finally reconstruct this image. So this is very, very useful, especially when you're talking about compression, for instance. This could also be, as you can also see, this could also reduce artifacts like noise and so on. So there are very nice applications of how you could use autoencoders in different ways. So with that being said, this is a straightforward like an autoencoder implementation. So here you have a sequential API with two convolution layers, and then that's actually flattened, the output of which is then taken into a dense layer, a latent representation of dimensionality 2. And this dimensionality is subsequently used to also reshape and then form a decoder. So I can also quickly, when we so when we see how this actually looks like, so we start with a sequential. So everything is basically implemented. So here we have an encoder and then the decoder. So here you see basically the complete representation of the encoder as well as the decoder is going in one single shot. So you start with the encoder, you complete the decoder, and your complete algorithm, your complete neural network architecture is defined straight away. And one of the things here is that it's probably compact, as you can see. But the trouble here is that in general, this does not let you, like, for instance, you cannot basically customize a lot of things. So for instance, if you look at how this entire structure would look like, say, the latent representation, right? if you look at how this actually the latent representation looks like on a 2D graph, then the distribution of the training images in the latent space actually looks a bit skewed. For instance, the reconstructed digits from some of the lobes here, for instance, in purple, would be pretty good. But since the distribution is irregular, say for instance, you see that there is an elongated green, also a space like it looks like a star. If you see, the trouble here is that not all of the reconstructions would then look really nice. So if you say, for instance, here this will look really nice. So all these lobes are very well formed, and but what we could do is here, if you look at say some if you take a reconstruction from this particular the green lobe or the yellow lobe, which actually looks elongated, then the outputs or the reconstruction looks pretty bad. And this is where we can naturally go from a sequential into some sort of like a variational autoencoder. But before we go there, I'll also quickly show you how this would actually look like. Say, for instance, if you implemented this on your own. So here I'm doing this, this implementation on, it's a very similar implementation. As you see here, we have an encoder encoder design here, the encoder architecture, and then the decoder architecture as well. And finally, when we actually run this, it's not really difficult because it's a pretty small data set as well. Here we are using the fashion MNIST data set, as you might probably have heard, or it's basically like the hello world of machine learning. So we moved from MNIST into fashion MNIST, and there are also much more better data sets as well available for doing a hello world representation or hello world for machine learning these days. But what we can then do is we can then see, say, for instance, here there is a handbag. If you look at how the handbag would then be represented, and if you reconstruct this handbag, then you will naturally see that it sort of like gets the handbag shape and the overall structure, but you see the autoencoder actually loses a lot of information. And for instance, yeah, so this is where a natural sort of like a step would be also, if you think about it, if you see this as a bug, but this could also be a feature, for instance, where you could also think of it as like a noise reduction machine. So this is where there are actually excellent papers on how you could actually use this as a noise reducing machine as well. And there have also been multiple implementations of how this could be used in basically reconstructing and compression as well. So this is where you see that the latent representation is simply a small vector. So we go from 28 by 28, a 784 dimensional vector into a 2-dimensional vector. So here, and this is all we need for this decoder to decode. So this is how cool the decoder is in this particular point. And this is where the overall algorithm itself is actually really nice. But as you see, it's basically one single shot. We have straightforward, we have like a definition, and then the direct the encoder as well as a decoder implementation in one single shot. So naturally, this is not really, sort of like a cup of tea for general researchers or people who would like to implement their own ways of loss functions and so on. And a natural problem here we actually see here is that because of this sort of like a distribution, and naturally the problem is also that reconstruction becomes pretty poor. And this is where a variational autoencoder could come in. And this is what do we talk about? What do we mean by variational autoencoder? Here we have a much better representation of how the distribution of the digits look like. So here we have much better like round shaped distribution here, purely because of how the autoencoder or the variation autoencoder learns as well. And there are also a lots of there is also a lots of information about how you could do this. But in this particular scenario, we will do this this implementation ourselves. So before we get into a lot more deeper, so there is also I think if you might have seen this, there is also a page called thisfaceisnotreal.com or something like that, where if you go in and then if you click on the generate face button. Basically, you could actually generate a face, and then basically it's an implementation of variational autoencoder. It's just a variation of that, and this is of course from DeepMind here. But the interesting part here is that it's photorealistic, and these are faces of people who do not exist. So these are purely from the latent representation, as we saw here, taking that latent representation and sort of like reconstructing an image, and then we get completely new images every single time. So this is one, like if with an input, you could actually produce like different faces, like photorealistic faces as well. And this is very interesting application of where a variation autoencoder could be used. When we're talking about, say, for instance, the variation autoencoder, so the difference here would be instead of going into a latent vector directly, we would then also sort of like have the mean and the variance of the probability distribution. So this is where the difference, the name of the variational autoencoder sort of comes in, where the instead of having this latent dimension, pure vectors, instead of that, we actually have the mean and we store the mean and the variance of the probability distribution. And what the decoder does is it just samples a latent vector from this distribution, and then it decodes the actual final, reconstructs the image, for instance. And in this particular case, we will also, going forward, we will also see how to build one with Keras, and we'll also try to show the design pattern, showing how we could actually go from the sequential API into the other forms of where we could actually extend all of this. So first of all, we will actually have 4 different elements over here. The sampling layer, we will see the variational encoder, the regularization loss, as well as the reconstruction loss. So here are the 4 components that we would like to actually bring into our existing layer, the existing architecture there you saw, right, in the previous case. What we would like to do is, if you see here, all of these functionalities are not available out of the box. So out of the box, Keras does not directly support a sampling layer or a variational encoder or a regularization loss or a reconstruction loss. What we would like to do is we would like to implement all of this and then bring it into our existing framework, existing neural network definition. And how we could do that is basically something like this. So this is where, in this particular case, we implement a sampling layer. So as you see here, the sampling layer uses like the mean and the variance. And typically, yeah, there is a definition of this layer as well. And we will see how to actually, this definition is available now. But how will we use this? We are going to basically implement this, and then we will see how we will actually bring it into the actual neural network definition. And this is where we come into the functional API. So as you see, sequential API has its own pros and cons, for instance. And now we see functional API. So functional API is extremely good at doing this sort of like customizations. And this is where we will see how exactly this customization would come in. So the functional API, when we use a functional API to build the model, what happens is this is somewhat similar to if you had used, more like an imperative programming. So you will write the layer definitions like so. So basically, you will have every layer would basically be a definition, and then it's more like a directed acyclic graph or DAG. Then what happens is you then individually then connect these dots together in the final model definition, as you see here. So first of all, we will have this encoder definition. The encoder model here has 2 output layers, one for the mean and one for the variation of the autoencoder vector, and then a custom sampling layer. So this is where we see that basically, if you remember the previous slide where we actually defined the sampling layer, and here this is actually completely custom written. And finally, these inputs and outputs are basically tied together in the model definition. So this is where one more cool thing is that the encoder input and then the output is now here multiple outputs. So you have the mean as well as the variation as well as the final representation, the sampling as well. So you have multiple outputs available, which could then be leveraged by the decoder to even build further on top of this. All right. So all of these are completely new. So these are something that is not available out of the box. We actually brought everything into the definition of the neural network architecture, and then we are going to basically use this to build our decoder going forward. So here's when, if you remember, in our third component, we have regularization loss. So this is yet another, something that a variational autoencoder typically uses, basically a KL divergence loss. This will basically keep the generated probability distributions in check. So basically, we would like to have it, similar in terms of the distribution, right? So this loss function would allow us to do such, have the distribution in basic check there. And the loss itself is built by applying a function to an intermediate values of the model. So this is where we would basically see. So here is basically the definition itself. So where we would like to see how all of this is actually there, but what we will actually see here is the KL divergence loss, basically the definition of the loss, and finally the encoder, basically the how we could actually add this loss layer into the actual definition of this encoder itself. So as you see here, we've actually defined the complete architecture, sort of like the architecture as well, and but now we are actually putting together independent things like what we would like to get from the architecture, and also define the loss function that the encoder itself will be using. So this is very, very nice. Here, what will happen here is that so the model itself will actually add all these losses in the end, but you see basically we have defined each of these independently, and we are slowly connecting it back into the neural network definition. So this is the really useful feature from the Keras functional API. It lets you do this sort of like separate implementations and then bring all of these together just before you're going to run the model or build the model. So having done all this, now we will finally compose the model. So this is where we will basically we will go from the model to from the encoder to the decoder, and then the encoder here will return three different values. Basically, the while the encoder simply requires just one, so it just needs one. And while the functional API, so with the functional API, you see that here we've defined all of this, and there's absolutely no issues at all, and just decode the correct one. So basically, we've had all the definitions in place. We simply define all of it, and then we define the model definition itself. So here we have the complete definition of the variational autoencoder in place with the encoder input as well as the decoder output. So we in some sense it's more modular. So if you want to make some changes, you can make it independent, and then here you'll see that the definition itself wouldn't basically change at all. So when we're talking about the training, so like I said, we will also have a separate like an implementation for the reconstruction loss. So in this particular case, the last addition for this variation autoencoder would be this particular definition of a loss function. So not to worry if this reconstruction loss isn't particularly, it doesn't make sense. But here you see basically we were initially, as you saw in the previous example of sequential API, we were using mean square error. But here we are basically using this reconstruction loss, which we can then pass it normally into the model compile. So here you see the model.compile or the VAE.compile basically taking in the loss as a reconstruction loss, where we also use this Keras metric. We compute this and then we provide it back into this particular loss function. And the metric itself here that it uses here is basically the mean square error. So having done all this, we will finally train. In this particular case, it's MNIST. But as you saw in the previous, in our example, we did fashion MNIST. It's not a much difference, but basically, it's basically providing a lot more challenge to the actual machine learning model underneath to do a bit more to actually try to reconstruct. And it's also interesting to see how the model can actually understand the structure and sort of reconstruct this, even given the fact that the latent dimension is so small. So this is the reason why you try to do with different data sets, and also you try to experiment and then see the results in the end, so that you can actually try to also understand the beauty of the architecture itself, and probably also try to come up with new ways of making sure that you can actually use this architecture for different other applications. So there is, I think, a question as well. So can we combine the sequential API just like encoder part and functional API in the same model? So typically that might not be possible because, as you see, the definition itself is the sequential is a lot more model defined, and you already have the model sort of like finalized. So in that sense, the output of the model itself would be a lot more difficult to probably combine with a sort of like a functional API. But you could definitely try that. That seems to be quite an interesting sort of like an idea that you're proposing. I would, if I think about it, probably, now that I think about it, it could be probably possible. So you have like a base definition of on a sequential API, and then you bring in the functional API where you would like to bring in, say, some customizations. It could be possible. I've not tried that myself. So probably, yeah, maybe if you already have an idea over there, if you'd like to try that out, it should probably be the only way I think it could probably result in an issue would be probably when the model could already be finalized, the graph would be finalized, and with a sequential API, that is what I mean, and functional API. Here you see basically the graph is not finalized until you actually bring in the model, the final model definition. So this is where I would still, I would hold my answer and probably maybe come back to you on a separately as well. But this is an excellent question. So I would like to try that out. And then at this point, I would say it's a bit challenging, maybe not, but I will probably also give myself an element of doubt and then say it could probably be possible. I will confirm that, and then I will keep you posted on what would actually be the result there. All right. So with that, I think so. You already saw that the functional API is quite already quite customizable. So what happens if we want to completely customize everything? So going from the definition of the class, if you want complete control over how you would like the model to be defined, how you would like to even override the training step, and so on, you could also do that. So that's where the fun comes with Keras here. So this is where the third design pattern that we would like to see here is where you would actually implement the VAE, the variational autoencoder, by actually subclassing from the Keras model class. So this is where most of the definitions of most of the frameworks that you would actually write, you could write it in such a fashion. This way, you have complete control, and also you could also define custom loss functions. Say if you have like a multi-output sort of like a scenario, then you could also sort of achieve that with this sort of like a complete subclassing of the model definition. So this is where here you see an example where the train step is also completely taken over. You completely redefine the train step. Here you also use the gradient tape and then apply the encoding step as well as the decoding step, compute the losses, and use the losses to compute the gradient and apply it. So you have like a complete control over here. And not only that, you customize the train step by keeping all the benefits of Keras and do pretty much similar. You basically do a model.fit, and but not only that. So there is more. So there is one more thing, as you might know. So the pretty cool thing part here is that you could also use it for distributor training, for instance. So here is an example for TPUs. But you could also use this for GPUs as well. So you could directly, fall back if a TPU is not available. You could actually, for instance, if you have like a GPU cluster, then the strategy could naturally fall back to a mirrored strategy to actually detect either a GPU or a TPU. So this is where it gets even more interesting about how you could train. So not only sort of like completely customize how the train step looks like, but also completely customize, how you could also do the distributor training on this particular scenario here. And of course, finally, once you're on a TPU, for instance, you could also, or a GPU for that matter, you also then completely train this. So here you see it looks a bit different. So the strategy scope, and then you actually define the encoder. Here again, it's very, very modular. So in this sense, if you look at it from a software engineering perspective, you could actually write unit tests for the create encoder method, write separate unit tests for the create decoder method, and then subsequently also check all of them together. So this actually actually becomes extremely nice in terms of how you could actually separate all of these steps and then ensure that every single time you actually get the same answer, when you're initializing the encoder or the decoder, or in your particular case, it could be anything. So the overall goal here would be to basically make sure that your software engineering, your complete the code base is completely tested, and you test every single method you actually have, and then write say, for example, if you're writing an integration test or a system test, here you will have everything in place. So you will basically build everything, and finally, of course, you do a fit. And so here you see that in this particular case, the subclassing API, sort of like the subclassing of the Keras model, sort of lets you gets you all these capabilities, and makes it easier for you to also maintain this sort of like code here. So this is the overall idea of how we would like to the three different strategies: the sequential, the functional, and then finally the subclassing the design paradigm. So I hope that was useful to you in the end. So I'm happy to also probably answer more questions if you have any. But I guess that would be my time. There are quite a few resources as well. I'm happy to share these slides, and then towards the end, and then I'm happy to also take your questions later on. But yeah, thank you very much.
Thanks very much for that, Karthik. It was interesting and very enjoyable. So I will bring Matthias on. There. So our next speaker is Matthias Face. I'm sorry if I'm pronouncing that wrong. I'll have to. And he will be talking to us about explainable AI beyond SHAP. And Matthias is talking to us from Belgium, I believe.
Yes, that's right.
We're getting a bit all over Europe, which is nice. It's nice that we have the possibility to do that with technology, and you have been a machine learning GDE for, you said, from nearly the beginning of it. That's very interesting. I'll let you go ahead with your talk then.
Great. Thanks a lot. Happy to be here. So I hope my screen is visible. Yes. Awesome. So basically, today I want to talk about explainable AI beyond SHAP. Basically with the whole meaning that based on the typical projects that we do, that it's typically simplified to just SHAP, and there's lots more to it. So that's why in this talk I really want to talk about those 4 topics. First of all, to start with the goal of explainability, what it adds. Then to talk about some projects and some learnings there. So I'll cluster them on the design patterns and some typical pitfalls. To have a look at tooling, like for example, SHAP as well. And then also some relevant research paper, just to give you some insights on what's out there, and to showcase that it's also a bit more than just SHAP. So first of all, the goal of explainable AI. It's basically on this workshop link shown below, is to really focus on the human AI complementarity. So regardless of the quality of your model, the problem at hand, it's really always about making sure that the human AI make the best use of both worlds. And like the typical use case, I would say, is that when AI is at par with humans, this is our typical use case. Basically, in this example, sometimes AI is right, sometimes the model is right, sometimes the human is right. And if you don't have explainability at that point in time, you basically lose trust, because it's hard to assess which one is really correct, which is a really big pity. If you can combine them correctly, it's really powerful. And the part of explainability here is to build that trust, to basically make sure that the model is used. You also drive adoption to keep on improving the model itself. So that's the typical use case. We also have 2 other phases, of course, when AI is weaker or the model is weaker than humans. Basically, this is the typical use case of having, during a training process, and making sure that the model and also the annotations are as relevant as possible. And one way is to use explainability here as well, to give some insight on why the model makes some decisions. And this way we can also give more examples of these hard problems. So basically the focus then is really on improving the machine, the model, and doing that as fast as possible. The other example is when AI is stronger than humans, it's still relevant as well to look at explainability. And this example, of course, of AlphaGo, for instance, in which you could really take some learnings and take, as a human, some insights on how the model is reasoning. So in both, in all examples, it's really useful. So that's a big starting point, because in a lot of previous examples as well, people would say explainability only is a necessity when it's like a legal requirement or something like that, whereas really we see it as it's always something to look for, going from active learning, going from improving model faster to really building trust when it's on par, or also thinking about how to bring the model insights to the people if the model is stronger. So that's really the goal, to make sure that you focus on the complementarity. It's a big one. And then to bring back the title, of course, it's also a bit more than adding SHAP. In essence, basically, the explainability is typically part of the project, not really only above the model. So that's a big decision, of course. That's a big difference. If it's part of the model, it's really focusing on the model part, whereas if you make it part of the project to make the project succeed, it makes us also very problem-specific. Given that the solution is very problem-specific. And that also means that from really the data set in which you work on until the model, until really the UI in which it works, all steps can take some explainability to see what you can do there, to make it more explainable, to again make sure that you have an increased adoption of the system, of the solution, of the model. So basically, this is really the main point of this talk. There's more than just the model itself. Again, going from dataset until UI, having the project and problem-specific context to help with that. So that's a bit the goal, how I see it about explainability. And to link this a bit to some projects that we did, I want to quickly go over some, I would call it, design patterns of things that are useful, that you can always take care of for every project that you start, starting with problem reframing, to interpret the models themselves, so things to consider if you're deciding which model to use, feature attribution, just like SHAP, transparency and transferability. These are also tools you can use to make sure that it's at hand, and then also making sure that you have some intuitive visualizations with some examples. I'll quickly go over them, going some examples, but please use the comments if you have any specific questions, which we can then tackle during the Q&A or during the session. The first one, it's really starting with asking the right question, of course. Makes a lot of sense, but sometimes we can forget this. I think the some trade-offs, the versuses, are things that we see at some projects that really made a big difference. An example is object detection versus classification. So a lot of computer vision problems, it's really a classification problem, but it can be very useful to make it an object detection problem that helps with classification. In this example of like detecting if a car is damaged or not, really showing where the damage is, can make it much more insightful, much more explainable, so that if it's not right, you can also understand why it was considered a damage. The next one is retrieval versus matching. Sorry, retrieval or matching versus ranking. In this example here, it's a project in which we need to detect the types of boxes, for instance. It's a bad picture maybe, but basically, typically inside the box, there's also a lot of types of contents, and actually there were like 10,000 types of classifications to be, types of classes to be picked from, which made it a very hard problem to really get completely correct. However, which was much more useful is basically if we reduce those 10,000 types to a top 3 pick of the most likely type, then basically the application itself became very useful and also very accurate, because the chance of the correct class being in one of the top 3 was of course much higher than one in the really the correct one, which makes it also very user friendly, and then also showcases a bit more like, okay, this is how you can use it. And it's a bit linked to the next one, automation versus augmentation, is to see really does the model need to perform it on 100%, or it can really just help to come up with some suggestions, in which case basically the interaction is much more natural. Last one is the regression versus classification. This is a project that is a bit small on the screen, but basically it's on a forecasting problem. And the idea was that we basically come up with some proposal or like a regression problem on trying to make sure that the predictions of the end of the month deals amounts would be as correct as possible, which ended up being a big problem given that we were at par with humans, meaning that either it was had the same prediction as a person, which then they agreed upon, it was not very useful, or we predicted something else, in which case they didn't really trust it. And if they don't really trust it, it's really hard to do something with that information. So really try to switch the problem and going from a regression problem to a classification problem and predicting for every deal what would be the most likely reason why it would not go through, and basically work on that and say, okay, this deal is probably less likely to convert because, for instance, the last activity was already 3 weeks ago. So that's a big reason why it would not be useful. Again, just doing something different, which avoided the problem of having a very unclear explanation of why we came up with some regression. That's a bit about asking the right question. Sorry. The next one is really actual ML model adaptations, interpretable models. So what can you do to make a model more interpretable? Basically, we have 3 main blocks, I would say. The first one is model decomposition. And this is something that's really hot, I would say, in research as well, is looking at a problem and decomposing it in smaller problems. And so in this example, it's one of the papers as well, is to see if we can classify the animals, but instead of really going to, again, one classification problem, you make it smaller problems, and this way it's also more explainable, the intermediate problems, and basically only the steps in between. Those are unexplainable, but basically the hierarchy of the problem sets, it's really an explainable thing. So there are some examples for that. For the next one, it's a bit linked to this, is hybrid AI, and it's basically combining manual rules with ML, or coming up with manual rules based on ML. That's also something that you can see in a lot of use cases, and it's basically, it's not always a requirement to completely use ML, but for instance, in this example, it's coming up with a type regex rules, but using ML to come up with these regex rules. So basically, the end result is a manual rule, but it's constructed using ML. Then the last one on like what happens for basically interpretable models themselves is a lot of advancements really going to make this distinction between high performance and high explainability, to combine that gap. So examples like TopNet, for instance, really are type of solutions, models that try to also have both situations, so you don't have to make this trade-off between high performance and explainable. So those are a bit the directions in which you can go for more interpretable models, things to consider to make sure that you check that box as well. Then, of course, the feature attribution or the well-known explainable AI solutions like LIME and saliency maps, or of course, a lot of examples, very useful. In this example here, it's in Dutch. Sorry for that. It's a website that we helped build. And then basically here, the idea was to come up with proposals of some properties that a certain company would like to buy. And instead of just showing the examples, we also used Shapley values to come up with the reasons why this would be a good match, which really helped in the end to make the model much more useful to the end customers. Of course, the deepfakes detectors are also a great example of using really saliency maps to showcase why or where some decisions are made, which is still very useful, those two examples, but it's not the only way to add explainability. Next is the transparency and transferability. This one, it's it's really starting from the data. It's a bit of doing really the logistics or the lineage, is making sure that you really understand what data you use to train something, that it can help with explaining why you have some reasons of making some predictions, but also in case, for instance, you had some bugs in the data collection, they can also quickly fix that based on you having the right metadata to showcase why or which dataset was used. So if there's an error on the dataset, or maybe you even base your model on some other model, and if you have the right lineage, you can really make sure that you can explain it as well, why some decisions are made. So that's one, using ML metadata, or basically some kind of system to collect the metadata on the data and then the models you use themselves. And then also, it's a lot about the data and model validation. These are two visualizations on this specific topic. It's basically to go beyond, for instance, data validation is really to understand your data pretty well. So you also know what kind of data space you are considering. And the model analyzer is doing the same thing, not just looking at your accuracy, but also looking at your accuracy for multiple types or segments of your data. To really have a better understanding of how your model performs, which also makes it much more easy to know how your model will perform on similar datasets. Lastly, on these types of things, the design pattern you can always reuse is intuitive visualizations. And basically, making it less of a mathematical problem, but really focusing on showcasing in a visual way how the model would think. So the biggest example is, of course, like just looking at the visual representations and showing for the model the most similar examples. So this example, it's about detecting some types of wood, in which as a way of illustrating why we come up with some visualizations that really showcase the most similar types of wood next to the first one. And this way, it's also easy for the people to understand why, basically, why we come up with some suggestions. The next one is attention-based visualizations, which was already showcased before, but it's still very visual, very clear, of course. Next is a dimensionality reduction. It's a bit similar to listing the most similar examples, but with having more dimensions, you can also see subgroups, which makes it very user-friendly to have a better overview of the complete space, not just of the most similar ones, but on also how the different pictures or texts or whatever kind of data you use are linked to each other. And then lastly is visualizing prediction outliers. It's a very typical thing to do as well during training, during annotation, to really help in looking at the outliers and focusing on them. Because if you can showcase yourself why something that we predict would be typically an outlier, it gives also more confidence that the non-outliers are also more correct. So these are typical things that we try to do to help. And of course, there are also some pitfalls. The biggest one would probably be causality versus correlation, which is typical for like more time series tabular data. That happens a lot. Those are mixed, and we try to correct that problem, of course. And the second one is the trusting the models on out-of-domain data. This is why the data validation and also model validation steps are really important to also make sure that, you don't ask for stupid predictions, that we know that data, and we can also predict something about that data example with a high probability of being correct. The correlation versus causation, probably I don't need to explain it, but of course, the very visual example of this is, of course, the hot weather causing both an increased demand in ice creams and an increase in sunburns. However, those two, of course, are just correlated, not implying any causation. So that's something that if you have domain knowledge, in this example, we know how the sun works. With domain knowledge, it's very easy to make sure that we don't make any wrong conclusions. But it's also typically a must-have is to have some kind of domain knowledge to make sure that you can take out the causation from the correlation, because it's not that simple to just fix yourself without any domain knowledge. And that's a bit like cost here as well. I mean, in the book of why, it's going from the typical ML use cases going really about correlation, association, seeing something and immediately being able to detect if it's something similar, but really looking at asking what if this or what if that, applying some kind of causations. It's really need to have this typical causal graph to be able to do that, which is really the next step. So that's really something different that we try to also visualize a bit more and seeing how we can help with that. The trust model on out-of-domain data, as mentioned before, TensorFlow data validation is a very good approach for doing this, and it's really for this example in which you have some kind of classes, and if it's really not seen before, it's hard to know which class is probably the best example. So it's really useful sometimes to consider this two-stage approach, in which you first detect if it's an outlier or not, and if so, then we typically have a different prediction, or at least a notion or a mention that it's really out of domain data. So it's not considered in the same way. So visualizing this here with a link to a YouTube video on the topic is really to make a two-step approach of detecting the outliers, and only if it's not an outlier, then really going with the model. Otherwise, you typically have other next steps. So with that, I basically quickly went over some of these design pattern and fit pitfalls. The main reason going over them is I believe that those are relevant for any project. So really for any project you start, you should be able to take some of those to help with explainability, and with helping explainability to really help to also have more users adopting the model itself. So that's really why I want to go over all of them. Next is, of course, the current tooling. Really like to refer to this cheat sheet. It's a very visual way of looking at it. Basically, considering the different blocks, starting with basically if it's only looking at the model decisions, if those are relevant, I really want to go into the model himself to understand it. If you have to go look at the model itself, there's a lot of feature visualization kind of approaches to really go into the feature space. But typically, it's really about the decisions that are made by the model. And then you have some options. Basically, if it's an interpretable model by design, you have some linear models, nearest neighbors, logistic regression, simpler models typically. Sorry, I was a bit looking at the chat. Sorry for that. So really looking at the linear models typically, which is not always that relevant, of course, but it really can be a very good choice if explainability is a must-have. Sometimes it's not a hard requirement, and then in those cases, the less interpretable models can be really better for your use case because they prevent a lot of more accuracy for your use case. And then basically you have three blocks. So if it needs to be a model that works on all models, then the biggest one, of course, is SHAP, but also Lime. Some other approaches are very relevant. And you also have some really specific example-based approaches to add explainability. So the most popular example is probably working with adversarial examples and seeing how you can really look at a model and how to make some examples that look very similar to us humans, but are very different from a model. So it's really an example-based approach to fool the model and also focus on those examples. But if you don't look for a model-agnostic approach, you can go a bit deeper into examples of how the model works. And then basically, this is where the typical examples of attention for NLP or these saliency maps from computer vision come into play. So this is really something that's looking at model-specific solutions, which can be a bit better if you know what kind of use case you cover. That gives a kind of a view on the typical really tools you can use to have a better view on explainability. So looking at the first one is, of course, SHAP. So it's really about this feature attribution. And then basically, looking at some assumptions, some axiomatic basis, making some assumption of how the model works, but it doesn't have any really domain knowledge inside. So it's really working on any kind of problem, which makes it that powerful and that also popular. So the cool thing is you can use SHAP for NLP, computer vision, time series data, but it's performing the best on tree-based models. So that's really the typical use case in which you go from the different types of features to really showcase which ones on an additive basis, which features are most important to come up with some suggestions. So that's the first one. Next one I really like is the Tigramite. I'm not sure if I'm speaking it correctly, if that's how you push it or pronounce it. But basically, it's looking at a discovery tool for causal relationships. And basically, it's not showing really causal relations, but really looking at proposals of causal relations. And it really does that by this PCMCI technique to see, basically do some kind of correlation test and also correlations with some time delays in between to see which features are really impacting which others. And then it can imply potential causation, which then it makes it much easier for domain experts to also validate if these kind of proposals make sense or not. So that's another tool that's really useful. UKI is starting the other way around, and basically you start from a model of the causations and try to use that for typical time series, which is also very, very useful, but really the opposite way of working, not coming up with suggestions of causality, but starting from a visualization of the causality to use that to add explainability. For saliency maps, just look at saliency. The TensorFlow package is a very neat overview of typical things you can use. It's in the same package, so really like that for computer vision projects. So that's a nice tool for that. The What If tool is something that's also out of the box available on GCP. So basically there you can use this kind of nice visualizations to do a lot of tests and also have very nice visualizations on what's in the data, and if you do small changes, and so a bit of the what ifs as well, what that implies for the predictions as well. For NLP, you basically have this language interpretability tool, which from our experience is really like the go-to tool to have a look at anything NLP explainability related. And then finally on Vertex AI, there's a lot of grained in or out of the box solutions as well that you can easily reuse. It's still a bit early days to have a look at those, but it makes it easier and easier to really get those visualizations out of the box. Then, given that I took a bit more time than expected, sorry for the switch in speed. Basically, I just wanted to go over 3 research papers, which I really liked personally. And the first one is on the context of computer vision. It's to make sure that there's some kind of sanity check as well for saliency maps. So basically, saliency maps are very cool to see what the probable place in the picture is that's very relevant. However, they can also be very misleading. And basically in this paper, they did some tests by really looking at randomizing the model itself. So basically on the right, you go more and more to a random model and then asking different packages to explain what kind of features the model used to make that prediction. We can see here is that basically, for instance, for GradCam, it really showcased, to detect the bird. It's looking at this place here, looking at the features. So it's basically, more and more random as well, going over the different layers, adding more and more randomization, which makes sense if you randomize it. That is basically doesn't contain a lot of knowledge. Versus, for instance, this guided GradCam, it really keeps on knowing where what was useful. And basically what they see in the paper is that it's really looking at just kind of outlier detection, or basically, not really showcasing what the model is thinking, just coming up with something that would make sense. So in effect, this kind of saliency maps and some examples, some implementations, it's not really showcasing what's relevant, it's just showcasing something that's plausible. So that's a really cool paper for that. Next one is this kind of this model decomposition concept, looking at how it can be useful for computer vision again. And they basically start with implementing kind of a feature engineering, maybe they're going a bit backwards, using deep learning, but decomposing it again into kind of features or concepts. So an example of like these zebras, they would say first, like detect stripiness of a picture, and if it's stripy or not, that could be a feature to basically afterwards take into account for your classifier. It's a very neat way of going back to the feature engineering, but then automated. But really adding a lot of explainability, of course, if you have these kind of features that people can also understand. This kind of similar setup is for neural back decision trees. But basically here, they don't define the features as something you can train directly, but they really start with word nets. So basically with a human-made kind of ontology to come up with these kind of features and how to split them. So basically looking at a dog, they would really start from animal, having more and more decisions based on the hierarchy or the relationships defined by word nets. So it's also a similar approach of going from one big black box model to a model that's really decomposed in smaller blocks. And that kind of direction is really something I'm really looking forward to see more and more. And I hope that would really help as well to make models more explainable. So with that, basically, I still have 1 minute remaining, and I hope it was a bit useful.
Thanks a lot, Matthias. I think it was definitely very useful for me. I mean, as a machine learning engineer, this is also something I would like to review in the future, and just give it a second look and learn all the concepts a bit in depth. So I think there are no questions in the chat, but definitely if someone gets this point and wants to ask any questions, may stick to the end. So speakers will still be here for answering any questions at the end. So if you guys just stick there and leave your questions, so maybe we can go through them later. But awesome. Thanks, Matthias. I think for me, it was great. So yeah, thank you so much for coming. Okay, see you then. Okay, so for our next speaker, we have Carl Weinmeister. Hey, Carl, are you here?
Hey, Ricardo.
How you doing? Yeah.
Oh, great. Ready to talk about AI analytics today.
Awesome. Yeah, I think that's also something that we're quite interested in jumping in. So yeah, I mean, I'm quite happy to get you started, and yeah, I'll leave you to start then. Okay, if you can share your screen, so we can put up your slides. That would be great. Awesome. Okay. Yep. There you go.
Okay, perfect.
All yours now, Carl. Good luck.
All right. Thank you, Ricardo. Hey, everybody. My name is Carl Weinmeister. I'm with Google, and I'm with our advocacy team, where we basically do a lot of these events worldwide. We focus on, my particular team focuses on data science and ML engineering. So today's talk is really a blend of data analytics and data science. So we're going to hopefully cover topics that might be applicable, even if you don't do a lot of deep data science like we just saw in the previous talk, that you can take advantage of some ML techniques. Also, if you are a data scientist, you might see some different ways to create models. It might be a little faster, or might allow you to build models in ways that your end users can leverage them more easily. So let's dive into what that really means. Okay. So the premise of this talk is that the AI skills shortage is still out there. We know, over the years, there's been a lot of question about there's not enough data scientists. It's hard to hire for, and that trend has not stopped. A couple recent reports I put here, one saying that data science is one of the most difficult roles to fill. The second was a report that showed that many companies aren't using AI because they don't have the lack of because they have a lack of technical expertise. Those skills are holding them back. So what we're going to talk about today are ways that a broader set of folks in the organization, maybe data analysts that are familiar with SQL, would be able to write some models and solve some problems. Maybe with not having some of the deep like Python and ML background, but still be able to build some useful models. And so kind of as a starting point, let's talk about spreadsheets as a source of a ton of data that's out there that is often used for just, keeping track of things or performing some calculations, not really for a source of doing ML modeling within the spreadsheet. So just, here you see a stat that 2 billion users are using G Suite. I just saw an article the other day that there are 1 billion installs of Google Sheets on mobile now. So it's just something that's everywhere and ubiquitous. And we'll talk about how to connect machine learning to spreadsheets. So how does data make its way into spreadsheets? There can be a lot of paths into that. Maybe somebody creates a report in some kind of business system. Maybe you're performing a query on that system, or you're using an API. In any case, of all these different ways, you're extracting data from a source system and then putting it into a spreadsheet. What are some problems with that approach? Well, number one, data freshness. So the data that's in the spreadsheet will get stale over time. It's a static view of the world. It's not something that's queryable with the most recent information. The second issue is data size. Spreadsheets often have a limit to how much data you can work with. And third, there's another issue to consider, which is security, right? So if you have a source table where you've authorized certain users to use it, and then you've extracted that data to a spreadsheet, well, what's to stop a user from emailing it to another group that wasn't authorized to view it? So once you pull data out of a main source system, put it in a spreadsheet, all the controls are lost around that. So let's look at connected sheets. This is a solution that brings together BigQuery and Sheets. So it kind of gives you the power of both. So it allows you to use Sheets for having a familiar interface, doing some streamlined analysis on data, no code, and BigQuery, which allows you to analyze petabytes of data very quickly. And this brings those both together. And if you're not familiar with BigQuery, a quick just overview, it is a Google Cloud Platform's data warehouse. It allows you to perform standard SQL statements to query immense amounts of data very quickly. And we'll later talk about some machine learning features that are built into BigQuery. And BigQuery is based on technology used inside of Google, allowing extremely high levels of reliability and availability. So that's BigQuery. BigQuery ML, which we're going to show off today, allows you to create all kinds of machine learning models in SQL. And you don't have to leave BigQuery to create these models. And let's look on the next slide, kind of shows a list of all the different model types, and there are many more coming. So you have your standard classification regression models, putting things in buckets or predicting a number, and different approaches ranging from logistic regression to deep neural networks. You also have time series forecasting and unsupervised methods like k-means clustering built into BigQuery ML. Okay, so let's start with the demo. So we're going to do 2 demos today. The first one, I just want to show a data set in BigQuery and how you'd access that in Sheets. So we'll start with that. So here we are with a public data set. This is the Iowa liquor retail set data set. It's basically just a set that shows sales over time. It's great for time series analysis. This is in a list of many different public data sets like weather, economic data, et cetera, that you can leverage from Google Cloud. So let's go into BigQuery and take a look at this data set. So here you see we're already seeing the schema for this data set. You can find out more information about, how many rows are in it, get a preview of the data. So we'll just go ahead and do a quick query of this data set. I'm going to select star here, and it'll just return me my queries, rather return the results here from my query. And you just see the different rows. I'll zoom in a little bit. Each of these individual rows is a transaction. These are wholesale transactions from retailers ordering the liquor, and they have the various, sale dollars and amounts and things like that. And so we can do things like group this data very easily. We could do something like, select date and sum of sale dollars, let's say, and then we'll group by date. And performing a query, did I get that right? Sale dollars, I believe. Yep. And that'll allow us to get more of a time series type of view on things. Actually, let's do couple more things here. Let's order by date. So we're in ascending order. Let's also give this a nicer title. So we'll just say total sales. And here we go, run. And there we go. So we're just quickly doing some analysis. This is putting the data in a grouped format so we could look at historical trends of what the sales are, look at seasonality and things like that. Okay, so that's BigQuery. Let's now look at connected sheets. So here we are in Google Sheets. And I've already connected the data set. So just to kind of make things a little faster today, to do that, I went to data connectors. I connected to BigQuery, and then I found that data set and are able to perform my query here. And you see here we have a preview of 21 million rows that we can work with, and I could refresh that. You see the different functions that you can perform with that data here. I'll just show you a couple things that I've already done. One is an extract here. So if I just wanted to, gather some information, maybe not the whole data set, I extracted some various columns here. I could apply filters, I could put a row limit, and then run that query, and then you're going to see it right here. And I can even refresh for the most recent data. I could create charts as well. And I know nothing super exciting here, but the cool part about this is the dynamic nature of it, right? So this is a chart at a point in time, but I can also refresh this chart if the data is constantly coming in to get more data, and my chart will actually change. Finally, what if I wanted to answer a question like, what are the top 10 liquors that were sold? Well, here we could do something like a pivot table. So here what I'm doing is I'm putting information like each individual item, descending in order of how much the sale amount was. And that's basically it. And here I have that information. So here you see where data analysts, without even leaving a sheet, can go and perform these kind of queries. Okay, so let's go back to the next part where we'll go deeper into machine learning. Okay, so let's take a case study in demand forecasting. So demand forecasting is applicable to many different domains. It could be transportation, where you're looking at ticket sales between different destinations. It could be in the media industry, where you're looking at different pieces of content, let's say, and trying to figure out which ones are going to be most popular, or understand maybe the number of active players in a game, those kind of things, or even telecom, where you're predicting network traffic. One of the most common scenarios is retail, where you think about how do you handle the right amount of stocking goods on the shelf versus the demand that's coming in for those goods. And it's an important problem from a business perspective, because you can have two different bad scenarios that happen if you don't get it right. If you have too much product and you're over allocating, then you're wasting money, right? You have product that spoils. On the other hand, if you have stockouts where you don't order enough, then you have a lost opportunity and you have missed sales. So getting these curves aligned is critical and a big source of optimizing profit. So let's look at an example using that same data set, using the BigQuery ML. So now we're going to move on from queries, and we're going to show how to create some machine learning models in BigQuery ML. So here's some of the transactional data that I showed you previously here. Let's look at how do I create a training set for that data. So you might do something like I just did before quickly, where I grouped some of the data. What we're doing here is let's basically break down each part of this SQL statement. First, we are selecting 3 different fields: the date, the item description, so we'll have various forms of liquor, various items, and then we're going to get the sum of the bottles sold. So 3 different columns. We're going to pull this information from the sales table. We're then going to group by both date and item name. So this is a little different from my query, where I just grouped all liquor types given a certain date. This will give you date and item combinations. So we'll be able to see multiple series or multiple types of liquor at different times. And finally, we are going to constrain the dates to about 1.5 years of data. So what might that look like after you run the query? Here are a couple examples, 2 different liquors, the Black Velvet and the Captain Morgan. It's not a lot of data you're seeing here, so you're not seeing sort of the long-term trends and seasonality, but you can quickly eyeball a couple things. Like if you look in February on Black Velvet, you see a similar peak for both 2016 and 2017. This is just showing you the data that we're working with here. This is our training data. This is what the data that we're using to learn patterns from in order to build a model. So how do we actually build a model? This is another statement that we'll walk through in detail. And I want to also point out that behind the scenes, there's a lot of great stuff happening to take a fairly complicated time series forecasting process and make it a lot faster and simpler. So there is a data pre-processing, things like outlier detection. There are holidays built into the various options, and you'll see that when we go through the clause. There are seasonal and trend decomposition, so even multiple layers of seasonality, right? Where we might see, yearly trends, we might also see weekly trends, and those can be stacked on top of each other, and it can detect that. It will also select the optimal statistical model parameters. It uses the ARIMA model as the base. It does a lot more beyond ARIMA, but it will figure out those PDQ parameters. It'll basically create multiple models and find the parameters that minimize the information loss. So you look at this different clause, the phrases here in this clause, and you see, first, we're creating a new model. Secondly, we're passing in some of the options. Let's go through some of these options here. First is a model type. We're putting in ARIMA. We could put, if it was a different type of data and problem, logistic regression, deep neural network, et cetera. But here we're specifying a time series problem. The next column here we're specifying is what's the date column, right? So we're just pointing to date. The next parameter is what data are we trying to predict? And that's the total amount sold. Finally, we, as far as columns, the ID column. So you could have multiple series in your data. So you might have, in this case, different types of liquor, each having parallel series, rows for each of the different items. But there are other scenarios. You might have maybe by country, or you might have by stores, things like that, as different multiple series in your data. You see holiday region. This is where you can optionally pass in, you know, some information that the data is applicable, in this case, to the US region, but you can see there are, you know, per country, per, you know, continent, various levels of regions built in, or rather holiday regions built in and supported. So you basically specify the parameters. You then run a select statement here where you're specifying which of the columns are you going to need from your training data. And that's it. So you just run that query and it will build a model for you. So how do you use that model? So once you've built it, you use ml.forecast. You point to the model name that you just created, and then you can pass in some optional parameters such as the forecast horizon, how many days forward are you going to train, and or rather forward are you going to predict. And secondly, you pass in the confidence level, which gives you this prediction interval. So it gives you a band of what you see shaded here in the diagram. Not only do you get the actual prediction, but you get a lower and upper estimates as well. So that's how ML forecast works. And now we've seen the three different statements, main statements. You also have an evaluate statement if you want to dive deeper into some of the metrics for building that model. So if you want to find out more about this demand forecasting use case, there are a couple resources. There's an article on the Google Cloud blog about this, and as well as a YouTube video. And we don't need to play it right now. So now let's talk about building something new. So we've talked about some of the building blocks. How might we solve a new problem with some of these tools? So let's just say that this is kind of a generic enterprise use case where you need to build a custom machine learning model, and then you want to share it with people throughout your organization. Your requirements are you want to build ML custom models quickly, you want to expose those to people throughout the organization, and allow users with little or no ML experience to run those models. So we're going to use the same technologies that we just talked about earlier in this talk, and we're going to add one new technology called AppScript. And AppScript, you can think of as the glue between different Google products. So in Google Workspace, that's Google Docs, Sheets, etc. It's a JavaScript-based scripting language that allows you to perform various tasks. And it includes libraries for Google Cloud integration, including BigQuery and various other functions. So you can have that integration between Google Workspace and Google Cloud. And so the just high-level workflow here is you're working with Sheets, and via AppScript, you're able to run those forecast functions to forecast and even train models. So let's now take a look at this. Okay, so I'm going to first point you to a sheet where you can, excuse me, this is going to be linked in my list of resources at the end. This is a demo sheet that shows how to build a type of solution that takes information sheets and connects that to BigQuery. Okay, so let's first look at the scripting in Sheets. So if I go to Tools and then Script Editor, here I am in the AppScript interface. And again, this code is in GitHub that you can look at in more detail later. This code is just JavaScript code that allows me to build a custom menu within Sheets. And within that custom menu, I can do things like train a model. If I click on the train menu item, it will run the train function here that'll define below. So I can train, I can forecast, I can do some configuration, I can override the GCP project I want to use, etc. So that's the functionalities built into this application. If we scroll down a little bit to things like, let's say, to forecasting, if you recall the SQL that we used before to create or replace model, the model name, the options, that's all here. We're just dynamically creating it. So, we're passing in, it's a model type ARIMA, and we're, again, dynamically passing in some column information from our spreadsheet, and then running that query, returning the data, and then putting the values back into the spreadsheet. So let's now take a look at how this works in the spreadsheet. So, excuse me, sorry, in this tab. So let's look at the example data tab. This is a time series here from the Google Store that has hourly visits to the Google Store during this time period of about a year and a half. And this is hourly data. And you can see this trend where it kind of goes up and then peaks and then comes back down and sort of repeats this pattern every day. Okay. So to create a custom model, you could do, the business user could do something like this by selecting all the data. And then we have this custom function we've added. We could train the model. It actually doesn't take long. It takes maybe 10 minutes or so, but I've already done that just to save time here on the training piece. So what we can show is forecasting. So we have all of this data, 8,000 different rows here, and let's try to forecast forward a few periods, okay? So let's say we want to forecast, let's say 5 periods forward. I can just say BQML forecast, and behind the scenes, what it's going to do is use the APIs to determine I selected 5 rows, so it's going to set the future time horizon to 5 rows, and then it will call the forecast method. It will gather data from a temporary table in BigQuery, and then extract that data, and then insert it into my spreadsheet here. So let's go ahead and run that. So running this script, and here you go. And you can see, just eyeballing it here, that you see that trend downward as we're kind of getting into the middle of the night, that the values start to decrease a little. So let's actually do a little experiment here where I've taken actual versus predicted, and I've trained on all the data except the last 3 days. So, and then what I did was predicted those last 3 days. And so what you see in this chart is that last week of data, just to kind of give a little context. We trained up until when the red part starts. And by the way, we trained, quite a bit of data before that as well. And then we're forecasting the piece in red. And we're comparing that against actuals. And you can see it does follow the trend very closely. So this data set happened to have, some patterns that were repeatable, and the time series forecasting worked very well for it. So this is basically time series forecasting in a nutshell, and how you could use that within a sheet. So if you could picture a scenario like this for maybe financial data or operational data, trying to connect that to machine learning models hosted by BigQuery ML or Vertex AI that I didn't get a chance to talk about much today. So let's go back to my presentation just to wrap it up. And the resources that we talked about today, the blog post, the code sample in GitHub, and the demo spreadsheet are all linked at this short URL, bit.ly/ml-sheet. And in the blog post near the bottom, it has links to the code sample and demo spreadsheet. All right, well, this wraps it up. Let's see if there's any questions from the audience, and also stick around for the segment at the end. So I can stop sharing.
Awesome, thank you, Carl. So yeah, I think, well, there are not much questions in the chat. We're still going to stick for all the other questions. So if anyone watching wants to ask questions about this talk or next talk, or like previous talks, please make sure to add those in the comments. In the meantime, yeah, we can just hang around, and maybe bring everyone up. I think Jana is also here with us, Matthias as well. Let me bring them up. Kartik still in the back, but yeah. Hello everyone. Yeah, welcome back to the stream. Kartik is here as well. Let's just have a quick chat.
Great. Thank you. Yeah, maybe the last question, last session, if I may, just a small question on the integrations in Google Sheets. I was wondering if there's any ideas as well on how to, yeah, you have the model predictions baked in the spreadsheets, how to expose them outside. Is it something that would be in the scope of these kind of products to expose them in the future as well, this kind of predictions as APIs, or it's really a separate kind of products?
Well, there are APIs for most of the, pretty much every cloud product like BigQuery, Vertex AI, right? There's, JavaScript, Python APIs. That integration that I was showing isn't direct. There's a BigQuery integration, and that's where I've saved a lot of work by using that BigQuery integration, because I could just use the built-in Sheets connector into BigQuery. But right now there isn't like a direct machine learning integration. But I can see that happening. I don't know if you've seen some of the demos from even like GPT-3 and things like that, where you have, let's say, a list of states or something, and it fills out the rest for you. I think there's just a lot of exciting things that can happen to bring like all the power of ML to business users. And that's why I kind of focused on spreadsheets, where there's just so much data that I think is not leveraging ML the way that it could.
All right, cool. And do you know, because you also mentioned like holidays, public holidays, that they also already like pre-processed, so that's part of like this kind of domain knowledge that you can give into it. Will also be something to see if, going forward, there will be kind of an interface to provide domain knowledge. So also something that might be interesting, but
yeah, that's a really good point. Yeah, the model that I built, that example, just sort of, I think I may have left out the option for holidays, but, absolutely passing in more context, like, holidays or any of the other options would be great. Yeah.
Thanks.
Cool. Definitely, it definitely makes sense. So I have one question for all of you. I know that most of the things we've discussed today, Carl, Matthias, and Kartik, I think, so all this information is like constantly coming up. New things are coming up. How do you guys keep updated in all this new things coming up? How do you guys do it? Because I'm quite interested, on like what you usually check up for new things coming up. What do you think, Matthias?
For me, it's a lot. It's two main channels. One is Twitter, just following a lot of people, the main one, and then also just at work. Given that I work in this context, there's a lot of Google chat groups on multiple topics. So just from colleagues.
Okay, cool.
Yeah, I think it's a similar case for me as well. It's mostly following a lot of people on Twitter, trying to find out what's happening there. Usually people share papers, implementations, quite a lot of things on Twitter. So I have quite a lot of lists that I follow. And yeah.
Okay.
Yeah, I mean, not a lot to add, but I think, through social media, and also just like, new projects, just always trying to look at, is there a new tool or a new concept I could apply to what I'm solving, and sort of hoping to sort of have a little bit of that reuse and using it in my day job to, with the limited time and so much out there.
Yeah, so much.
Yeah.
is definitely so much out there that we can actually use. So sometimes I get overwhelmed, but I'm definitely gonna follow all you guys on Twitter and turn on notifications in case you retweet any interesting things. So yeah.
How do you? I don't get how. Well, I don't know yet myself, but like how to filter through all the information, especially on like yes, social media. I find that it's always, but I'm a beginner myself, but it feels very overwhelming, like knowing how to, everybody wants to like shock you. It's like, oh, this new thing, but like knowing what is actually like a proper development, that's I imagine that's hard. Okay, Matthias, can I ask you a question? The academics versus industry. Are you happy with that? So I just read in your bio that you were doing a PhD and left it for industry. Are you? Of course, I imagine you're happy with the change, but is it a different kind of? How do you find the difference between the two?
Yeah, I'm personally very motivated if I see what I built to be used somewhere, which is a bit more immediate, of course, in industry versus doing research. So I was really happy to do research at that point in time, given that there were not a lot of industry projects going on with ML. But for me, it's really a personal thing. So for me, I really like to apply it and see cool paper. Let's see how I can use it versus coming up with a new paper based on the previous paper. But it's really like a personal thing.
Very good.
Maybe just to add to that, it's because a lot of new colleagues as well, they see, it's solved. Somebody solved it in some paper, and it's like, we can't do the project, it's already solved. But then it's funny if you really want to apply it somewhere, there's still a lot of things to solve. So it's really a different challenge.
Yeah, it's always great to see it, like when everyone's using it, and when you get the chance to build the solution, not only the technology but the actual solution. It's the combination of both, as you said, is kind of like quite exciting for all software engineers. So I think well, maybe we don't have too much questions. I think it would be it would be great if we could be in person and just have a chat and have a drink and discuss further. But I think hopefully that by the end of the year we can all get some normality and maybe running some in-person events. I know, well, right now, we're all over the world, but hopefully we can all meet again. But so if there's any other further questions, I think we might.
We type very fast because we're going to cancel the broadcast.
Sure. And if people want to double check, this will be updated in the YouTube videos, so you can just check the chat. I'm definitely gonna double check a few of the talks and look them more calmly. So feel welcome to do it as well.
Thank you so much for speaking with us. It was an honor having you here. It's very nice. As some of the people commented in the comments, they were excellent talks. Thank you all very much.
All right, thank you.
Okay.
Thanks for the opportunity.
Thank you for having us. Yeah.
Thank you.
So thank you for joining us.
Have a good day.
Okay.
You too.
See ya.